Hello, here we are again so soon because I didn't want to cloud the issue with the cases that we went through last time. So I'm going to transform all that stuff from video 24 into this video, which is now video 25. Based on these observations, we can actually simplify the way we even draw the pictures. So I'm going to call this, I've relisted the data so that we can go through this again. It's exactly the same data, so you don't have to copy that down again. But we've got cow, pig, dog, pig that we want to insert into our dictionary. I'm going to call this cases revisited or cases revised. And case one was when we had an empty tree. The before picture was we had a root, which is a pointer, and it pointed to a single external node, except observation. The external node is empty, thus it's a waste of memory space to dynamically allocate a node and put it down here and eat up some of our memory. Let a zero pointer stand in for an external node. Boom. Our binary search tree now consists of a single external node. It looks like it doesn't consist of anything. It looks like it's just a zero pointer pointed to nothing. But in our minds, when we run into a zero pointer in our implementation of this, we're going to say, we have encountered an external node. So you can visualize the little pointer to the little square down here, and maybe that will make it easier to follow through the algorithms that we're headed toward with this thing. After. Well, we're inserting cow the very first time, so that's the very first thing to go in the tree. And note one, observation one says in each successful put, this one is going to be successful, there's no cow in this tree yet. It's replacing an external node by an internal node with two external kids. Watch how this picture boils down. We still have the root. The root is a permanent private variable, by the way, a la the head, cursor, tail, except binary search tree has even fewer private variables. Really, all we got to do is hang on to that little star at the top of the tree, and we got it. So the root is the only private variable we need. We're going to replace the zero, the external node, with a pointer to a new internal node. In this case, the cow. There. With two external kids. Well, look at this. Even the external kids, those are represented by zeros. That's it. There. We inserted the new node in an empty tree. Case two. I might even have room for all the cases. I'm still going to need to draw a line. Case two, I'm going to do a real fast and nasty before, since we're saving space. See how not explicitly representing external nodes saves space? It even saves whiteboard space. So I can do the before picture. Root points to cow, to zero or external kids. Now then, the after picture. By the way, case two is new whichever. You've already got the cases written down. I won't write those down again. But case one was a new root of the whole tree because we didn't have anything. Case two is a new right child because when we compare the key for this gigantic value here, the picture of the pig, the key for this value is pig. Pig is greater than cow, so we need to look. Here's a step I left out. We first need to look before we leap. Is there anything over there? We are looking either to find pig in the tree, in which case we return false and we're done. We don't send anything back. Or we are looking for an external node. When we run into an external node in our search to do an insertion, that means stop right there, replace that external node with a new internal node. Here we go, very deliberately. Pig, the key pig is greater than cow. So we look and see, you know what, that's an external node. I'm going to replace that external node with a pointer to the new data value being inserted. Root. Root is still cow, permanently cow. No left child. Now we replace the right external node with a pointer to a new node. And I take back what I said. I don't think I'm going to have room for everything on the board, but I'll give it a shot. Pig. And pig has two external kids, so both of the initial values there are zeros. It's kind of like the sentinel value 0 as the next pointer at the end of the linked list. Remember, tail arrow next is always 0. Except we're going to have a lot of end of the list here. I mean, this tree could go off every which direction. We could have zeros all across the bottom. Those all mean you've reached the end. You've reached the bottom of the tree. Whenever we reach the bottom of the tree, when we're doing an insert operation, that means that we found the place for the new data value to be inserted. Comparing the keys as we go left and right. So now, that's the after picture for this one. Case 3, I'm just going to keep on going. Case 3 is to insert dog. When I insert dog, D is greater than C, so I go this direction, D is less than P, and I look and see, look before I leap, and find out that, in fact, there is no left child over here. So instead of a new right child this time, there'll be a new left child. So the after picture in this case will be root, points to cow. Cow, you're going to need to get shorter. There's not going to be room for everybody else. There. Short cow. Left child still 0. Right child points to pig. Right child is pig. I stated that incorrectly. And dog. Dog replaces that 0 pointer. I stated that wrong too. The external left child of pig is replaced by a pointer to new internal node with dog in it. And dog has 2 external kids left and right. There. So the picture's cleaner. I don't have all those little squares hanging off the bottom. But remember, whenever I run into a 0 pointer at the bottom of the tree, that means I've encountered an external node. And the reason I'm browbeating you to death on that is because almost all the recursive algorithms you see about binary trees and binary search trees, they talk about external nodes as the base cases. So when we run into a 0, we'll just say we run into a 0, that's the base case. We also interpret that as running into an external node in the tree. One more. Case 4 was insert pig. Here we go. Pig is greater than cow. Pig is equal to pig. That doesn't mean they've got exactly the same picture. It doesn't mean when all the values are the same. It means the keys match. That's what's key. That's what's important. If the keys match, we throw it out. Return false. And I did the picture again for video 25. Now, what else is there to say about that? Believe it or not, here we go. There is something else to say about that. This actually has a very subtle implication that I have not been bringing out. This business of in each successful put. I could have said in every successful put. It's always the same. In the implementation, here's a weird business here. In the implementation, there's really only one case. In every case, when we successfully insert a node, we are replacing a 0 node pointer with a new pointer to a new node in the tree. I am just not stating things very well today at all. Let me see if I can try that again. In each successful case, we are copying over a 0 node pointer with a pointer to a new node in the tree. There, I like that a lot better. Each successful case, replacing a 0 pointer that's already somewhere in the tree, we're replacing that 0 pointer value with a pointer to a new node for the newly inserted data item. I'm going to do this backwards. Look, going from here to here, I replaced the left child. I highlighted that. That's hot pink if you can't see the color. But I replaced that with a pointer to the new node dog. Now, let's switch color. How did I get here? Well, I replaced this external right child, also known as a 0 pointer. I replaced that value with a pointer to a new right child, pig. But wait, there's more. Green that'll show up well enough. What did I do here? Well, it looks like that's an outlier. That's a special case. The tree was empty. No, it's not a special case. I replaced a 0 pointer in the tree. It just happened to be the root. I replaced that with a pointer to cow. So now, let me go through that again in a forward direction. Each successful insert, I hit a 0 pointer in the tree. I do that right off the bat if the tree is empty. I hit a 0 point in the tree, freeze, okay, here I am. Replace that 0 pointer with a pointer to a new node. Done. 0 got replaced with a pointer to cow. Insert pig. Okay, here I go. Let's look for pig. Pig is greater than cow. Oh, look. Ran into a 0 pointer. Freeze. Replace the 0 pointer with a pointer to a new node that's got pig. One more time. That was so much fun. Dog. Dog is greater than cow, less than pig. Oh no. When I try to go to the left, I run into a 0 pointer. Freeze. Replace the 0 pointer with a pointer to dog. Why am I making such a big deal out of this? Who knows? You know, you could ask that about just about everything I do. The reason I'm doing this is because the simplest, most straightforward way to do the put operation is recursively. If it doesn't match, if the keys don't match, then put it in whichever direction it goes. Put to the left or put to the right. How do I put to the left or put to the right? I recursively call my put operation, passing in either the left or the right child pointer. Let me say that again. Put is going to call itself recursively. Put. When put hits a 0 pointer, as in this example, I called put, I passed in the right child because pig is greater than cow. That's what made me determine that I made the recursive call that goes to the right. I pass in root arrow right, else I pass in root arrow left. So I pass in root arrow right. Oh, base case. When I hit a 0, that's an external node. That's the freeze. Don't go any further. When I pass in a 0 pointer, I stop right there and replace that with a pointer to the new node. Let me say that again. Put is recursively calling itself, passing in either the right child or the left child every time. Okay? Think of this. Recursive put function. The base case is, if the pointer you pass me is 0, then I'm going to stop right here, replace the 0 with a pointer to a new node. So when I'm trying to insert pig, I compare pig to cow, it's greater. So I misstated before. I'm going to have to undo some of the wording. I wish there was some way to go back and edit the video just to take out some of the talking. I said, we will look before we leap, and if it's a 0 pointer, no. In recursion, the weird thing is, you go ahead and leap. You go ahead and go there and deal with it when you get there. So I'm not going to look in advance and say, oh no, I'm headed toward a 0 pointer. Since pig is greater than cow, I go ahead and pass in the right child and let the recursive function call deal with it. Now, here I am, started all over, recursive function call. Somebody passed me a 0 pointer. That means that's where this new node goes. So I replace the 0 pointer value with a pointer to the new node. Watch this. Now cow and pig are both in there. Let's insert dog. Recursive call from the public wrapper calls the recursive overload. Here we go. Dog is greater than cow. I make a recursive call, passing in root arrow right. Now, for all our recursive call knows, remember it's always taking a local point of view, it thinks that pig is the root of the whole tree. It thinks that's root. That's probably the best name for the parameter that I'm passing in. I'm passing in the root of the subtree that's rooted at pig. Now it compares dog to what it thinks is the root of the whole tree. Is dog greater than or less than pig? Dog is less than pig. So I don't make the recursive call to the right, I make a recursive call to the left. And it goes this direction when I'm inserting dog. Passes in the 0 without even looking at it. It passes in the left child of pig. When it gets inside the recursive function, test the base case, and it's 0, says freeze. Don't go any further. If I try to go any further down the tree, I'm going to crash. So I'm going to stop right there and replace that 0 pointer with a pointer to whatever's being inserted, and in this case, it's dog. Okay? It's going to be that way throughout the entire set of inserts. What's weird about that? What's weird about these two, at least so I'll claim, is in each case, all the recursive function is doing is replacing a 0 node pointer with the address of a new node. That's all it's doing. It doesn't know if it's adding a new right child to the tree or adding a new left child of the tree. But wait, there's more. First call to the public wrapper. It turns around and calls the private overload, passing in the root of the whole tree. Passes in the root of the whole tree, which at the very beginning is 0. Our recursive function tests this base case. If someone just passed me a 0 pointer, I'm going to stop right there and replace that 0 pointer with a pointer to a new node. Our recursive call, when it passes in the root of the whole tree and there's nothing there, that's a 0 pointer. Your constructor better initialize root to 0. A whole tree root, that'd be a better name for this, because root might be the recursive function parameter name. But at any rate, we pass this in, test the base case, it's a 0, stop and replace that with a pointer to the new node. Sounds like I'm repeating myself. I am. This case, new right child. This case, new left child. This case, new root of the entire tree. They're all the same. That extremely local point of view that the recursive function takes doesn't know if it's appending a new left child to the tree, if it's appending a new right child to the tree, or if it's putting the very first node in the entire tree. It does not know which of those it's doing. Because what we're going to do is pass in a pointer to a node by reference, which is going to give us the power to change this from a 0 to a new node pointer pointing to a new node, change it from a 0 to a new node pointer pointing to a new node, change it from a 0 pointing to a new node pointer, regardless of where that pointer is. Whether here's the recursive views. Here's the recursive functions point of view. Someone passed me that. Someone passed me that. So I'm going to stop there and replace it with a pointer to a new node. Here's the recursive function in a previous incarnation. Somebody passed me that. I don't know if it's their right child, if it's their left child, or it's the root of the whole tree. I don't know. I don't care. Someone passed me the address. By reference, they passed me the address of a variable. There should be pointing at a node, and it's not. It's a 0. So I'm going to replace it with that. I'm going to make it point at a new node. Here's recursive function talking again. It just can't shut up. Someone passed me this. Someone passed me a pointer to a node variable by reference, and I checked it and found out it's a 0. So I'm going to stop right there and replace it with a pointer to a new node. The separate cases are for our benefit so that we can draw the picture and check and make sure things go where they're supposed to. In terms of how we design the put function, there's only one case. Base case. Well, I take that back. No, there are 2 cases. I'm sorry. One case is they passed it in, there's a 0 pointer. I replace it with a new node, return true. It was successful. The other case is they passed me in pig again. I forgot about this one out here with the tail on the wrong end. They pass in pig again. The base case there is going to be they match, in which case I stop and return false without appending a new node to the tree. So I revise my earlier comment. There are 2 cases, but there are not 4 or 5 or 6. Our view is because we are taking this global view of what's happening to the tree as a whole. Oh, look, a cow has a right child and pig has a left child and all that stuff. The recursive function point of view is I'm just either putting a new node right here or it matches and I'm not. That's all it knows. That's all the recursive put function knows. It's amazing. And I told you that part of the art of designing recursive algorithms that are correct and clean and efficient is taking an extremely local view. All I know is I have a pointer to a node that I'm supposed to do something with. That's all the recursive function knows. And then it has to look and see if it has to pass in recursively the left or right. And I've kind of talked around it in a circle. I put a boundary around it. Next time, let's see if we can be a little more deliberate about what's going to actually have to happen in the put function. Okay, see you online.